Hello and welcome back to the CCENT journey with me, Ryan, and in this section we're going to go over IPv6. For those who don't know, you can contact me here on YouTube, on LinkedIn or Twitter. So first of all, we need to understand what IPv6 actually is and why do we need it. So first of all, there are a few things that unfortunately we do need to remember about the protocol. So it is kind of a bit of a memorization side of things, but it's important that you do remember these because obviously if we are going to be tested on some of the fundamentals of IPv6, we would expect to see some of the kind of basic facts about it. So we know a lot about IPv4. We know that it's a 32-bit address field. So each of those, remember those zeros and ones that we talked about previously? There's 32 of them. And we know that each octet is a single byte, and since we have 4 octets, we have 4 bytes in total. So we write out an IPv4 address, like so. We know that each of these are a single byte. We've discussed this in depth in many videos previously, and we know that in a byte there's 8 bits, and since we have 4 bytes in total, it's 32 bits. So hopefully you're comfortable with that. If you're not comfortable, go back and watch the IPv4 videos, which are earlier on in the course. Now the reason we sort of are bringing up IPv6 so late in the course is because from my experience, you're going to have kind of a bunch of different engineers taking the CCENT. Some are going to be in the industry for some time, and due to lack of familiarity, they're not too keen on IPv6, I find. So it's important that you kind of do it at the end of the course, in my opinion, because it's the last hurdle to overcome before the exam. The other part of it is if you're a new engineer and you're looking at Cisco from a fresh point of view, I think it's really good to learn about kind of networking today and IPv4, and then when you learn about IPv6, it's easy to understand where that fits in. So when I say to you IPv6 is a new IP protocol at layer 3, you know, because of how far you are in your studies so far, you know about the OSI model and you know how that works and how it interoperates with each other at different layers. So when we're talking about something new at layer 3, instantly you're thinking, as a CCENT candidate, what about ARP? What about all these other protocols like ICMP? What about all of these that we learned already? So it's better for me, from my opinion, and from feedback, to do it towards the end. So moving on then, what do we need to know about it? So we know, again, there are 4 bytes, 32 bits in IPv4, while there's a total of 16 bytes, which is 128 bits in IPv6. So to give you an example of what that looks like, this is a IPv6 address. So you'll notice that, first of all, it looks very interesting. You can see that instead of octets, we have these like semicolons that split the addresses up. And you're also going to notice straight away something very odd. Some of these have 4 numbers, or 4 hexadecimals, I should say. And you'll see what I mean by that shortly. Like, for example, D and B. And then you're going to also notice that some of them are only having 1. So we have a single character between the 2 colons. So this is important to understand because, again, being able to identify a IPv6 address is one thing, but trying to identify a correct IPv6 address is another. So no doubt that people are going to give you, especially in an exam environment, wrong addresses, and you need to be able to identify that. So it's important that we look at an IPv6 address and be able to identify a valid IPv6 address. So digging deeper into this 128-bit address, so we know that there's a colon that's used to separate a group of 4 hex characters. So here we can see that there are 4 characters and there's a colon here. Now next to it there's only 3 and there's a colon, and even next to that there's only a 1, and we'll get into why that is shortly. But important to know that normally there are 4 hex characters. Okay. Now hexadecimal, very similar to what we've seen previously with our MAC addresses at layer 2, it's hexadecimal is actually a base 16. And what do we mean by that? we mean it has 16 values, which are 0 all the way up to 9. So obviously 1, 2, 3, 4, and so forth, up to 9. But once it hits 10, it becomes a character. So A, 11 is B, 12 is C, and that will continue to go up till F. And in total, that's 16 characters. So that's why we call it a base 16. So instantly, if we've seen here something above like a Y, for example, we instantly know this is not a valid IPv6 address. So something to keep in mind about this base 16, make sure you memorize the 16 placeholders that you can have with hexadecimal. So there are 4 bits in a single hex character. So every single number here, or character like a D, each of these are 4 bits. So if you add up each of these, you again get 128 bits. Now that's obviously assuming that when you add this one up, there's 1 represented there, but there's actually going to be 4 in there. Okay, so in total, there are obviously going to be 16 bits. So 16 bits between each colon. Now, if you've seen IPv6 before, I might be teaching you kind of some of the basics here, but this is what you need to remember, especially when they're going to give you some of these questions in some of the exams you may be taking in the future. It's important to remember, okay, there's 128 bits. Each colon represents 16 bits. Each hex value is 4 bits in itself, and I know that hexadecimal is a base 16. So that's what we've learned so far. What else do we need to know about IPv6? So why is IPv6 even needed? So we know in IPv4 there's a lot of addresses. We also know that there's not many left. In fact, I'm pretty sure that RIPE, the actual organization that controls this, has handed out the last IP ranges. So because of that, we use features that we've already learned throughout the course, like NAT, and we also use addresses in the RFC 1918 space. So this is the private IP ranges. Remember we talked about those, the 10 dot, the 172.16, and of course the 192.168. We use these private ranges with the NAT address space, so we would have multiple addresses overloading or patting to a single public IP. Well, that was put together, this whole solution of NAT, this technology if you like, was put together primarily to combat the exhaustion of IPv4. And we've talked about that in some previous videos. So IPv6 is the long-term goal, which is ultimately to get people onto IPv6. And there's actually some interesting websites out there that shows you the percentages of people that have moved to IPv6. Some ISPs, depending on the technology you buy from them, will give you IPv6 addressing. And some protocols, like Chrome for example, will try and use IPv6 as a default moving forward, if it's possible. So there is some really interesting stuff already going on with IPv6. Now it's certainly coming. It's been coming on for many, many years now. You'll see that IPv6 was dated many years ago to come out, but it's taken a long time to kind of have that motion towards moving to IPv6. And the reason for that, again, is because things like NAT was invented to help slow down the exhaustion of IP addressing. And even though RIPE is handing out its last ranges to individual companies, organizations, internet service providers, it doesn't necessarily mean that those companies haven't yet exhausted the IPs that they were given from RIPE. So there's still a lot of IPs out there floating around, and IPs can be traded between companies and so forth. But for now, we need to understand that IPv4 is kind of coming to the end of its lifespan, if you like, and IPv6 is going to be the future. Now, the beauty of IPv6 is now we know a lot about things, for example, like RIP, and we know a lot about static routing. IPv6 is extremely similar to this. So for IPv6, we have something called RIP-NG, which is the Routing Information Protocol next generation, which is the new version of RIP for IPv6, and we have things like OSPF v3 that supports IPv6. Now the beauty of this is the underlying use cases and protocols themselves, like how OSPF creates a loop-free path throughout the network. Those sort of algorithms, behaviors, and configurations very much stay the same. It's just some of the minor changes and improvements that IPv6 offers. So obviously that's outside the scope of the CCENT, but it's important to know that, okay, we've moved away from IPv4, we're moving towards IPv6. Everything you've learned about IPv4 really isn't gonna impact what you're gonna learn about IPv6. In fact, it's gonna help dramatically, because if you can do it for IPv4, you can do it for IPv6. Now some of the syntaxes are different, but the underlying foundation knowledge is there. So why do we need it? We need it because we've exhausted the IPv4 space and we need to move forward. And with things like IoT, the Internet of Things, where every device needs to have some sort of connection out, like fridges, cars, and so forth, we're only going to increase the need for IPs because we have more and more and more devices connecting to the network. And again, that is the drive behind IPv6. So we know why it's needed. We know why it's kind of been delayed because of protocols that were created like NAT, and we understand how it's visually different to IPv4. Again, I can't stress this enough, but make sure you remember like the key things of why it's different and how it's different. So how to express IPv6. Now IPv6 addresses are complex and long and tricky to write and remember. So we've just seen that. We looked at one example and it was a lot longer because it's 128 bits and it has hexadecimals, so it has more potential values. So again, we have to remember a lot. So there's a few tricks to minimize the overhead. So what I mean by that is we have some rules that we're allowed to apply to our IPv6 addresses in order to make them smaller, easier to remember. And that was why in the previous slide we saw between two colons a single character like a 0. So there are some rules that we can do, and these rules are important to remember, to understand, and to practice. So the first of the rules is called leading zeros. So leading zeros. In each word, part, portion, whatever you want to call it, each 16 bits, a leading 0 can be omitted. So what do I mean by that? Well, we've seen that we know that each between each colon there's got to be 4 characters, whether that's a B, or a C, or 1, 2, or 3. There has to be 4. However, if, for example, between these two colons you have something like 0012, then what this rule allows us to do ultimately is to remove these zeros and allow it to be presented like so. Now, because we're only allowed to remove leading zeros, the actual underlying application is able to look at this and assume that because we know that there are 4 characters between each colon, that there must be 2 leading zeros missing. So for example, if we had 0002 between colons, then we can remove the zeros and leave a single 2. Now it's important to remember that only leading zeros can be removed, because if we start removing zeros all over the place, the application, protocols and so forth won't be able to identify where those zeros should have been. So only leading zeros can be omitted. So that's rule number 1. Pretty straightforward. Rule number 2 is called zero compression, and that's a single set, notice the word single here, of consecutive zeros can be replaced with a double colon. So a single set, so we can't do this twice, and it's the only time you'll see a double colon. So what do I mean by that? Let's have a look at the example that I've got here. Here's an example of a IPv6 address or written out. So it's long-handed, and we can see that each of these are obviously going to be our 16 bits. We can see they're represented, or sorry, they are broken up by these colons. And we know that based on rule 1, things like this here can be completely replaced with just a 4. But notice also that we have a lot of zeros. We have zeros here, quite a lot of them, and they're all consecutive. But we also have a bunch of zeros here. So notice it only says single. So this means that we can't get rid of all of these zeros and all of these zeros and replace them with a double colon. We can only do it once. And by default, it will choose the largest consecutive zeros. So let's look at an example of if we apply both these rules to this IPv6 address, what actually happens to it. So it ultimately becomes much, much, much smaller. Very easy to remember now. So let's have a look at what's happened. Well, first of all, this here, we've applied the rule number 1 to it. We got rid of all the leading zeros and we replaced it with a B. Now, since this is all zeros, we can't just get rid of it fully. So we still need to have a single zero to represent all those zeros. Now notice here, the 4. Again, we can get rid of this and replace it with just a 4. And then the single set of consecutive zeros, are all here. And they were replaced by this double colon. And then this here, because the zeros are not leading, we can't get rid of them. Because again, the application and protocols wouldn't know where to insert them back in. So that had to remain the way it is. But look how much smaller we were able to condense that long 128-bit IPv6 address down into something much, much smaller. Now this is something that you need to remember. Both of these rules you need to know and be able to take an address like this and make it much smaller. And the opposite is true, to be able to take an address like this and put it back into its original form. You also need to identify any incorrect hexadecimal characters. Like, for example, if someone put a G there, we would know this is not a valid address. So the main thing to take away from this video, which we'll cover obviously on the review, is some of the facts that we've talked about IPv6, how to apply these rules, and unfortunately having to remember each of these individual facts about the protocol. Okay, so that's all we've got time for. And just to sort of summarize what we've done so far, we've now actually seen our first glance at an IPv6 address. So they look scary to begin with, but once you get used to them and start using it on a regular basis, you'll find it's pretty much the same. It's just different. I say that in the sense of all the protocols that you've learned about are the same. It's just different addresses. And once you get used to using IPv6, it becomes sort of much kind of what you're used to ultimately. It's important that we remember the bits, the lengths, the hexes. So again, it's hexadecimal, base 16. Remember how long it is. It's 128 bits. How many bytes it is, and how many bits are inside each of those colons. Important here, those rules we've just gone over. Make sure you understand how to express an IPv6 address in using the shortcuts and what those shortcuts actually are. The rules around those shortcuts, like it has to be consecutive zeros to replace it with the double colons, and you can only admit the leading zeros. I would then highly recommend you look at some IPv6 addressing and practice actually putting them into the shorthand and then putting them back into longhand. Now it seems pretty straightforward, and it is. It's something you need to remember, and the only way to remember things is repetition and repetition of doing something. So I hope this video has been informative, and I'd like to thank you for viewing, and if it has been, please do like and subscribe.